Hello everyone. So today I am going to present on the topic kernel trick in SVM. So we will see what exactly the kernel trick in SVM means. So most of the data in real world is not linearly separable, but the SVM algorithm, which is support vector machine algorithm, which is a classification algorithm, works best with the linearly separable data. But as we come across the problems in real world, the data is non-linearly separable. So SVM becomes confused here, and here the transformation is needed. So kernel rig comes in picture here. Kernel rig in SVM helps SVM to separate the nonlinear data and to handle the non-linearly separable data. So let's see the first slide. So many datasets are not linearly separable in their original feature space. SVM works best with linearly separable data, so it does not work its best with nonlinear data. And kernel rig helps SVM to handle nonlinear decision boundaries efficiently. So, what exactly the kernel trick does? It transforms the data into high dimensional space by using feature mapping. So what exactly is feature mapping? Let's see. Data is transformed into higher dimensions where classes may become linearly separable. So in feature mapping, the data from lower dimensions is transformed into higher dimensions. That's when the data becomes linearly separable, and SVM already works best with the linearly separable data. So what exactly the kernel trick does? Instead of explicitly computing new coordinates while transforming into higher dimension, kernel functions in kernel trick directly computes similarity or inner products in higher dimensional space. Here are there are four types of kernel functions, which are linear kernel, polynomial kernel, RBF or Gaussian kernel, and sigmoid kernel. So, in that, the linear kernel is the simplest type of all, which works with the data which is already linearly separable. And the other three works with the data which is non-linearly separable. The polynomial kernel captures the polynomial relationships among features and then transformed it into higher dimensional space. While the RBF kernel is effective for highly complex and circular pattern. As we see in the first slide, there are two concentric circular two concentric circles. In that the data is uh, data is there, so we can't transform it using a simple SVM trick. So here the RBF kernel helps us to transform the data or to separate the circular pattern data. Then the fourth is sigmoid kernel, which is similar to activation function in neural networks. So these are the types of kernel function. For example, the polynomial kernel is used in the XOR problems where we need to separate the nonlinear data. Then we will see how exactly this kernel trick works to separate the non-linearly separable data and to transform the data into higher dimensional space. So SVM has a decision function which is based on dot products between data points. So kernel function replaces these dot products with a nonlinear function, enabling a higher dimensional separation. As you can see in the diagram, the SVM has a hyperplane which separates the class A and class B. But using kernel trick, we transform the data into higher dimensions, and using a simple hyperplane, the data is transformed into two separate classes. So here we use a formula which is given like k of xy is equals to phi of x into phi of y into k of xy, where xy are the input vectors and phi is the mapping function, which is a nonlinear function, which is the main point which helps to enable the higher dimensional separation. What exactly the strength of kernel trick is? It no need to compute the higher dimensional coordinates separately. So it reduces the increases the computational efficiency of the SVM algorithm. So here are the challenges and limitations of kernel trick. First challenge is kernel choice is critical, as there are no universal kernels that are given for the data. So according to data, the kernel choice changes. So that is a task to choose the kernel which is will be best for the data. Then it is computationally expensive for very large data set. If the data set is very large, it becomes computationally expensive to calculate the kernel functions in higher dimensional space and to separate the data. Risk of overfitting: if parameters are poorly tuned, as we can see in the diagram, there is overfitting. Wrong kernel may lead to excessive overfitting. Then less interpretable compared to simple linear classifiers. We can interpret the simple linear classifiers in SVM simply, but we can't interpret the kernel functions simply. Kernel trick makes SVM capable of handling nonlinear classification problems. It uses kernel functions to implicitly map data into higher dimensions. The strengths of kernel function are it is versatile, powerful, and it makes the SVM computationally efficient. Then limitations are it requires careful kernel and parameter selection. If it does not, then overfitting or underfitting can occur, and there are no best results of the algorithm. So that's all about the kernel trick in SVM. Thank you.